Yeah, we'll continue. So, so I'm going to start with a short summary of last time, not too long. So let's start with the motivations again. So I told you 3 motivating examples, and the first one was matrix multiplication. And there we are interested in this matrix multiplication exponent, right? It's this number, which we know is between 2 and something like 2.37. And
write a bit bigger, it's good for the bigger.
Little bit bigger. And this exponent is given, you can give it as follows. You can say 2 to the power omega. This is so-called asymptotic tensor rank. We will revisit these definitions, but it's the asymptotic tensor rank of a small tensor, matrix multiplication tensor. That was the first example. Second example had to do with communication or information theory. It's about Shannon capacity. Yeah, and I gave you this example of the 7th cycle, which is there's an open problem about the 7th cycle. 2, 3, 4, 5, 7. C7. And here we would like to know what's the Shannon capacity of C7. And let me write down one definition. So it's a supremum over n of the independence number of the nth power strong graph product power of C7, and then the nth root. And here we know, and just to give you an idea, here we know we have the following bounds which are not tight. Or at least one of them is not tight. Yeah, and the third example had to do with set, the game set, or the cap set problem. I didn't say much about this. I only gave the example, so I will give it again, and we'll talk about it later more. So the question is, what is the maximum size of any subset A in Z 3Z to the n, such that for any 3 elements x, y, z in A, there are no u and v in Z3Z to the n with v non-zero, such that the triple x, y, z is equal to the triple u plus v, u plus 2v. So yeah, so this means they're on a, this would mean they're on a line. Yeah, so A is a set without any lines.
You want to say there are no uv?
Yeah. Oh, sorry. Yeah, exactly. And here we know bounds. So there's this lower bound by Adel, and then so we're interested in what happens asymptotically. So I'm looking at the maximum size of such an A asymptotically.
What is the low now?
2 point, I think it's 2.4. Actually, I'm not sure. Maybe it could be 2.2. Actually, I'm not sure. It's a result by Adel. Doesn't matter much. It's not tight. 2.4. Yeah. Let me just write Adel. I'm actually not sure about the bound. But, can look it up. So these were the examples, and then we looked at. So there's a duality theorem by Strassen. So let's quickly. It's a duality theorem, also called Strassen's spectral theorem. So this was this abstract theorem, right? And we can apply this theorem to these settings. So what's the abstract theorem? Let me quickly recall this. So you have a semmering, and on the semmering you have a pre-order. Don't worry if you don't know what this. I'm not going to use this, but just to recap. There's this pre-order, which has to be a Strassen pre-order. And then, if you have this data, what you define is a rank of any element A in the semmering, which is the minimum number n, such that A is smaller than the sum of n ones. So the element 1 is in the semmering, I take it n times. It's the element n. And you can define the opposite notion, it's the subrank. It's the maximum number n, such that I get n, the same n, from A. And then you define the asymptotic spectrum as the set X, S, and then the pre-order, as the set of all maps from the semmering to the reals that are multiplicative and additive. So let me just write their homomorphisms, semmering homomorphisms, from the semmering to the non-negative reals. And I also want them to be monotone. So if A and B, so for all A and B, if A is smaller than B, then phi of A is smaller than phi of B. And then there's Strassen's theorem, the duality theorem. And it tells us three things, under some mild assumptions, which we just don't talk about now. So it tells us three things. You have this asymptotic notion of a pre-order. So an smaller than bn plus little o of n. If and only if for all phi in the asymptotic spectrum holds that phi of A is smaller than phi of B. And so if you want to understand this asymptotic notion of these asymptotic relations, then you should understand this asymptotic spectrum. And if you care about, so let's look at rank and subrank again, so you can define.
But in all these problems, we care exactly about relationships like that. We don't care about losing low.
Yes, we care about these asymptotic behaviors. And to make it a little bit more precise, so you can look at the asymptotic rank of an element A, which I define here as the infimum over n of the rank of A to the n to the power 1 over n. You can look at the opposite thing, the asymptotic subrank, which is the supremum over n of the subrank of A to the n 1 over n. And Strassen's theorem, if you have this, then you can prove that this equals actually the maximum over all phi in the asymptotic spectrum, which I just know by x now, of phi evaluated at A. And this one is the minimum over all phi in x of phi evaluated at A. So this is naturally like a minimization problem, and then we can write it as a maximization problem. So that's like the duality, and here's the other way around.
So Jeroen, I asked you this question privately, but
yeah.
Do it again. The Strassen pre-order has this condition that every element has a finite rank. I mean, there is an upper bound.
Yeah. Yeah.
Rank of every element in the semi-ring. Is it possible that the duality will hold for a subset or subring of elements for which such an upper bound exists, and sort of ignore the others?
Well, if you can just restrict your attention to a sub-semmering, then you're definitely fine. Then you can just do it.
No, right.
Rank will be defined in a different way.
But if the elements that happen to have a finite rank form a semmering, a sub-semmering, then you will definitely be fine. But maybe
I'm still when I'm doing this, comparison comparisons, I will need to compare them to other elements in the ring. Yeah, sure, if I just could restrict myself completely.
Yeah, but maybe what you're thinking about is not like that. Maybe your elements are not a subsaharan.
Yeah, maybe they are not a subsaharan.
And then I'm not sure. And then probably there are some counterexamples. But yeah.
But the elements that have finite rank will always form a subsaharan.
Yeah, I think so, but you need a little bit more than just finite rank,
No,
the
but
third property.
May not be defined there, or it may not be. The pre-order, I mean, yeah, sure, there will be a subsaharan, but the pre-order may need all the elements.
It's an interesting question to see what we can relax. Yeah, it's an interesting question. Yeah, it's not clear, not immediately clear. So this is Strassen's theorem, and so let me just mention the two instances that we discussed, and we're going to continue on those instances. So the first instance of a semi-ring with a preorder is tensors. And by tensors, I just mean order 3 tensors, yeah? So cubes of numbers. And on these tensors, we have a direct sum and a Kronecker product, tensor Kronecker product. And as our units, there's an additive unit, which is just an empty 0 dimensional tensor. And there's this 1 by 1 by 1 tensor with an element 1 in it. So that's the tensor semi-ring. This is all a bit abstract, but just want to make the connection. And we had this pre-order here. We said S is smaller than T if there are 3 matrices ABC of the right format such that we can obtain S from T by applying A, B, and C to T. Let's make this a little bit more clear again, because otherwise maybe it gets confusing. So T and S are just, they're 3-dimensional arrays. Yeah, and when I write this, what I mean is I can write it as a sum like this. It's a multilinear combination given by these ABC. So this is the ijkth entry of this. This is the definition, right? So you take this. This goes over ABC. Just to make this clear. Yeah, and so that's the first instance. And the second is graphs.
So formally, what do you mean by the set of tensors?
I mean, yeah, it's like a union. Yeah, just a union.
All 3 dimensional arrays of all sizes.
Yeah, maybe you can just say.
You kind of identify n by n with a subset of n plus 1 and n plus 1. You don't do this.
Say it again.
So.
If you want to really be really formal, what you want to do is you want to identify isomorphic tensors. I didn't, but I mean, yeah. So just all dimensions. Graphs was the other example. So here we look at all graphs, and we take a disjoint union as an addition, and we take the strong graph product as a multiplication. And we have like the empty graph, and we have the graph with a single element as our units. And this is the semi-ring pre-order given by graph homomorphism. So G is smaller than H. By definition, if there is a graph homomorphism from G bar to H bar. And so graph homomorphism is a map on the vertices that sends edges to edges. Yeah? And the point of this definition was that if you now take the subrank and you apply it to this instance, you get the independence number of a graph, which is the size of the largest independent set in a graph. And if you take the asymptotic subrank, you get the Shannon capacity of the graph. You can also take rank and asymptotic rank, but we'll do that later. Okay, so Strassen was really into tensors, and this was my addition to the theory to look at graphs. And maybe I'll mention one more quick thing about the general theory. So we had this interaction. I showed you this interaction theorem between being additive and being multiplicative. And actually, the way I knew about it is that I met Noga Alon in the elevator, and he told me about it. So that's, but he heard it from someone named Holtzman. It's very much related to the Schoenager-Tau theorem, but I hadn't thought about it like this before. So the statement is that for any tensor, for any elements A and B in this general setting, if the asymptotic subrank is multiplicative on these two elements, then it's additive and the other way around. So that's a pretty interesting statement, and you can apply this to Shannon capacity, for example, and yeah. And then this other theorem that I mentioned.
But it doesn't hold for rank.
Oh yeah, it also holds for rank. Yeah, also holds for rank. Yeah.
But in all examples, we know it just it just doesn't hold typically.
Well, yeah, I haven't thought about it much. I don't know. Yeah, so yeah. I don't know which examples explicitly, but I mean.
Yeah, no, I guess here it was non-trivial to come up with examples where it doesn't hold.
Yeah.
In the case of Shannon capacity, it was non-trivial to come up with examples where it doesn't hold.
Right.
And in tensors,
there it's not so hard. I have there are examples. Yeah. So there was this subsaharan theorem, which is nice, and we'll use it today.
So let me just ask a question. If you take if you take a set of elements so that it holds for every pair, then it's a semi-ring.
If I take a subset of my semi-ring for which this holds,
yeah,
for all pairs, right?
Is it an interesting one?
Maybe, yeah. I don't know.
It's probably not. Yeah.
It's a good question. Yeah. So the subsaharan theorem, it says that if I take a subsaharan S of my semi-ring T, then the asymptotic spectra are related as follows. So the asymptotic spectrum of S. So there's also a pre-order on T, so I can restrict it to S, and I can obtain all elements via a surjection from asymptotic spectrum of T. This is pretty abstract, so don't worry too much. But it's just saying that if yeah, so I can if I have an element here, I can restrict it to S, and I get the element here, and all elements here come from this procedure. It also says if I have an infinite family here, then I know that there must be an infinite family here. For example, yeah? We're gonna see this later. I gave a bad example last time, which is wrong. You can look that back on the internet. With matrices, that was not correct. So that's the summary, and let's continue with the graphs.
You should mention as a simple example that if we were looking at matrices and not at tensors, then this set X is just rank.
Yeah, that's a nice example. Yeah, so let's just let's mention that. If instead of tensors you take two tensors, so matrices, and you take the direct sum and the tensor and the Kronecker product and the diagonal matrices as your natural numbers, then you just get matrix rank as your only element in the asymptotic spectrum. Yeah. All right. So let's continue with something new. So elements in the asymptotic spectrum of graphs. So the goal will be to show, well, I'm not going to show everything, but so I'm going to tell you about like 4 examples of elements in here. The first is the fractional Hammersbound. this one actually depends on the field, so you can do this over all kinds of fields. So you actually get an infinite family in the end. The second one is the Lovastatin number. Then we have the complement of the fractional orthogonal rank, and we have a fractional Clique-cover number. And these are contained in the asymptotic spectrum of graphs, meaning they are maps from graphs to the real numbers, and they are multiplicative under the strong graph product and additive under disjoint union, and they are monotone under this pre-order that I defined for graphs. Okay. Now, somehow, to me, when I look at this, there are somehow two types. There's this fractional type, and then there's Lovastatin number. So let's start with the fractional functions.
So maybe you didn't say it explicitly, but maybe some people were not here last time. I mean, this is useful if you want to get either upper bounds or lower bounds on these parameters. In this case, I guess we are looking at upper bounds on Shannon capacity.
Yeah.
So if you understood all these spectra, if you knew them all, and you could evaluate it,
that's right.
max of them will give you the.
So all these elements will give upper bounds on Shannon capacity. If we would know all elements in the asymptotic spectrum of graphs, we would actually be able to compute Shannon capacity. Well, assuming that these maps are computable, right? So that we don't know, but mathematically, we would reach Shannon capacity. Yes. So let's start with these fractional functions. So these fractional functions, they come from non-fractional functions. Namely, let's see how to do this.
Non-functional, you mean integer programs and linear programs?
Yeah, but I'm going to do it in a different way. But you can do it like that, but I don't want to do it like that. So we start with the Clique-cover number of a graph, chi bar, which is the minimum number n, such that there is a map f from the vertices of G to n, such that for any u and v different that are not an edge, holds that f of u is different from f of v.
An easier way to say it is the chromatic number of the complement.
That's right. It's the chromatic number of the complement. I have another board. Yeah. So that's the first one. Somehow I think this will be useful to do it like this, but we'll see. So the complement of the orthogonal rank is the minimum number n, such that we have a map f from the vertices of G to vectors in Rn that are non-zero, such that for all u and v different and not an edge, holds that f at u and f at v are orthogonal. Yeah, so that's some kind of variation on this one. Well, it's also easy to see that one is bigger than the other, that this one is bigger than this one. So let me mention now the third one, that's the Hamersbound. So given the field F, we have a Hamersbound. At G is defined as the minimum rank of a matrix. So M is a matrix over F indexed by the vertices such that for every vertex V holds that MVV, so the diagonal is non-zero. You could also say equals to 1, that will be the same. And for any U different from V, not an edge, we have that m uv is 0.
What was the name of this again?
This is called the Hamer's bound.
Hammers is the name of
Hammers, okay, yeah.
This was written after the Lovastatin, right?
That's correct.
Yeah, the same definition of the matrix appears in Lovastatin's.
That's also...
Not over arbitrary fields, he's using just...
Yes, and he doesn't look at the rank.
He doesn't look at the rank.
You'll see it. We'll see it later. Yeah, so these three functions. And so the lemma, so let me state the lemma. These three functions are submultiplicative, additive, monotone, and normalized. So that's somehow, so these are all the guys, all the maps from graphs to the reals that are multiplicative, additive, monotone, and normalized. These three almost satisfy it, but here you have submultiplicative. Okay, so we need to fix this, but this is already pretty good. So let me write it down. Lemma. The above are submultiplicative, additive, monotone, and normalized. So in particular, there are also upper bounds on the Shannon capacity. Okay, this already gives you upper bounds on the Shannon capacity. Let me just prove. I'm not going to prove this lemma, but let me prove one consequence. Proof of the fact that this is very simple, so that the independence number is smaller than the Hamer's bound. Yeah, just to practice. So what you do is you take an independent set in G, and you take a feasible M in this minimization. And then what you do is you look at M and you restrict it. You restrict this matrix to the coordinates of your independent set S. And well, what you get then is, because on the diagonals we have non-zeros or ones, and on the non-edges we have zeros. So we get actually a diagonal tensor or identity matrix, I should say, not tensor, matrix. So this is an identity matrix, so its rank is the size of S. Yeah. So that's that gives you this inequality. So it's pretty simple. And then so let's do one example with the 5 cycle. So what we need to do is we need to cover it with cliques. That's sorry. What I want to do? I want to do the clique cover number. That's an example. Yeah, I see. Example. So the 5 cycle, what's the clique cover number? Just wanted to do a quick example. Well, so we can cover it with 3 cliques. Okay, so that's the clique cover number of the 5 cycle. It's at most 3. So we know that the Shannon capacity of 5 cycle is at most 3. All right. So that's non-fractional, but we want it to be multiplicative somehow. That seems to be the right thing to do. So I want to have fractional parameters. And here's what we do. So lemma, if phi is submultiplicative, additive, normalized, and monotone, then I define a fractional version of this graph parameter as follows. It's defined as an infimum over D, where I take the graph G, and I'm going to take a lexicographic product with KD bar. So what this means is I replace every vertex of G with D vertices, and I replace every edge in G with a complete bipartite graph. That's the definition for now of this. Yeah, so I'm blowing up every vertex of G into D vertices, and there are no edges among these. It's KD bar. And the edges of G become complete bipartite. I apply phi to this and I divide by D. Okay, so that's a new graph parameter. And then the lemma says, then, so this fractional parameter is again submultiplicative, additive, monotone and normalized. So let's not prove this, but let's apply it to the 5 cycle. So I take the 5 cycle and I want to take D equals 2. So every vertex becomes 2 vertices. And I get complete bipartite graphs. Like this. And now I want to look at the fractional Clique-over number of C5. So I need to now cover this guy with cliques. And you need only 5. Yeah. So let's just, yeah. There's a nice way of doing it. One has to go outside. So I can cover this guy with 5 cliques, so I get that this is at most 5 over 2, because I blew up with D equals 2. Yeah, so that's already better than what we had before. Okay, so, but now, yeah, so we're still only submultiplicative, it seems. So let's...
Something better about taking D equals 3?
No.
D equals... No, so this... Yeah, I think this is it for... I'm not sure how to prove it to you, but you need the dual program to see it. Yeah.
In the Clique-over case, you get
Yeah. So here here it comes. Yeah. That's right. So yeah. So here's the lemma that tells you when it works. So let phi again be submultiplicative, additive, monotone and normalized. Now, if for all G and H holds that phi evaluated at the lexicographic product of G and H is at least phi evaluated at the lexicographic product of G and K phi H bar. So this you already know what this means, because I told you. Yeah, so you blow it up with size phi H here. This is like the more general definition. That's lexicographic product. So now you don't put, you actually put some edges in the blow up.
What is I mean, if this is not an integer, what do you do? Phi of H?
Yeah. Okay. So we have to assume it's actually a natural number. Yeah. In this lemma. Yeah. In this lemma, phi goes to natural numbers.
Can you take the flow value or something?
I don't know.
Doesn't make sense.
Didn't think about it. I've only applied it to cases where it's integer. Then phi of f is in the asymptotic spectrum of graphs. So
But this is a weaker property than actually having it be a semi-definite program. What you wrote, or this is. I mean, in general, like Clique-over, fractional Clique-over is a
Linear
program.
program.
In fact, and
Yeah.
it has duality and
yeah,
it has multiplicativity, and it's non-negative, so
yeah.
multiplicativity is easy. So you write this condition is more general.
Well, it will apply to all these.
Yeah, to all of them, but I mean, I'm just wondering if it's more general
being a linear.
Or semi-definite duality. That there are situations where it's not.
Well, for the Hammersbound, for the fractional Hammersbound, we don't know whether it's a linear program or a semi-definite program. But it does have this.
Okay.
Yeah. So I'm not going to prove this, but I'm going to state the application. So this is by Boeg and Cox. And also, yeah, Shannon worked on the fractional Clique-over number and other people. Using this lemma, you can show that the fractional Hammersbound and the fractional complement of the orthogonal rank and the fractional Clique-over number are in the asymptotic spectrum of graphs. Yeah, so the only thing you need to do, really, to prove this is to check this this condition. So let's check it for the Hammersbound, at least.
It's possibly worth mentioning that it's fractional bounds, in the case it do give linear or semi-definite programs, they are used actually in graph coloring algorithms or approximations of, it's not just abstract parameters to study Shannon capacity. I mean,
Yeah.
The best algorithms to approximate chromatic number use this vector coloring. So
Yeah, the fractional Clique-over number is a linear program, but it's a very big linear program. I will mention this actually later. And the Lovastatin number is an STPU, so we'll see that later. Yeah. Let's try to. So I want to do a proof of this for the Hammersbound. So I want to take. So I should actually define the lexicographic product then. It's a pretty simple procedure that you need to do. So, yeah, so the lexicographic product, how it's defined, the vertex set is just a Cartesian product of the vertex set of G and H. The edge set of the lexicographic product is given by pairs, of course, such that either GG prime are an edge in G, or G equals G prime and HH prime are an edge in H. Okay, that's the definition. Yeah, so you see this block, this recursive structure somehow, lexicographic.
just put copies of H
Yeah.
in the blocks.
Yeah. So now we take a feasible element for this minimization here. So remember, this is a minimization over these matrices. And now in this case, because we're looking at this this lexicographic product, we get like a block matrix. So let's just think of it as a maybe 3 by 3 block matrix. So in G there will be some non-edges, and there we will have zeros, like 0 blocks in a block matrix. And
what is the inside and what is the outside?
the outside is, so the outer structure, the block, like, yeah.
Every block is a copy of H.
Yeah.
Okay.
That's right. Yeah, so if in H, if in G you have a non-edge, then you get a 0 block. Yeah, because, and if there is an edge in G, then you can do whatever you want. So I get stars. And on the diagonal, you get matrices that are feasible for the Hammersbound for H. Yeah, because then we're in this case where G equals G prime. So then, depending on H, we get zeros. We will get some zeros. On the diagonal, we get like 1s or non-zero elements. We will have some stars. And so here happens the same thing. Now, I claim this is a feasible. So yeah, let's say this is a feasible matrix for this minimization. I want to turn it into a feasible matrix for for this minimization. And the trick to do it, that's maybe the most important thing I want to tell you, is Gaussian elimination. So Gaussian elimination means we're going to take linear combinations of rows and columns in order to, what we're going to try is in order to make these diagonal. And you can do this, and what's going to happen if you take linear combinations, this 0 block will stay 0. This star block will stay star block. So it's not messing with that. Yeah, so you can turn this using Gaussian elimination. This will stay 0. Stars will stay stars. And we can make these diagonal, and you will get, so you get a couple of 1s and then 0s on the diagonal. How many 1s will you get? Well, it depends on the Hammersbound of H. Okay, so you will exactly get the number of 1s is exactly the Hammersbound, or is at least the Hammersbound at H.
Yeah, I mean there's a factor of the number of vertices in G or something.
I think the number of 1s will be at least this number, because this has to fit on H. Hope I'm doing this right. I think this is the main idea. Okay, so let me just mention. Maybe I skip this. Right.
Couldn't you prove it intuitively?
Tell me.
In the following sense, I mean, phi is in the spectrum of graphs, right? So it's supposed to control the Shannon capacity.
Phi is submultiplicative.
No, but yeah, but we take it. Oh, this is just any. Well, no, but you are looking for phi. You are after the Shannon capacity, which is the independence number of this graphs and graph products. If you are adding edges inside this copy, then the independence number just goes down.
Right.
So it's
So when you're looking at the ratio, yeah.
there's no ratio. It's not the fractional. It's not the fractional. Or you're thinking you wanted to write fractional.
No, that's right. Yeah, I see. Yeah, good.
So does this last lemma prove it that the spectra is infinite for graphs?
No, not yet. No, you need to work for that. So Boog and Cox do this. So that's another result. I just wanted to mention this now. Let me write it here. Let's just say it. So this gives you infinitely many points, but you need to prove that, right? So you need to prove that these are different. They will maybe not all be different, but what Boog and Cox prove is that for different primes, for different characteristics, you would get different elements, different functions. Yeah, so that shows that this is an infinite set. They were the first to show this. So let me maybe skip this. Yeah, we've covered that. Let's go to the Lovastatin number.
So just in the set of graphs, we have a subsemi-ring of the perfect graph.
Yeah.
And then we have only.
Yeah, but it's not a subsemi-ring.
It's not a subsemi-ring.
No.
It's not what.
I think it's not multiplicative. I checked this once.
It's not multiplicative, and so strong product doesn't give you a perfect graph.
Not always. Yeah.
Yeah.
Yeah. I checked this once. Okay.
Maybe you took bipartite graphs. It's mostly this top of a trivial example.
Right.
And then you get one element in the.
Yeah. So let's do. So these were the fractional parameters that we know, and now there's the Lovastatin number. And let me state the definition. So it's defined as a minimization over the maximum eigenvalue of matrices M, and these are real matrices indexed by the vertices. They're symmetric. On the diagonal, we have 1s, and on the non-edges, we also have 1s. So yeah, it looks a bit like the Hammersbach, but it's different. We're not looking at rank, we're looking at the maximum eigenvalue. So it's a different function. And the really surprising result is that this is by Lovas, that this is in the asymptotic spectrum of graphs. An interesting remark is also, that's also really special, is that this function is computable as a small semi-definite program. Okay, so the fractional Klikover number is computable by a large linear program, so we know it's computable. The fractional orthogonal rank, I don't know. Fractional Hammersbound, I also don't know. Meaning, I don't know whether they are computable. And but this one is actually efficiently computable.
I think the fractional, the vector covering number is a semi-definite program.
Is it? Okay.
Or if you want the minimum dimension, sorry, I'm not.
Yeah, that's yeah.
No, if you want the minimum dimension.
Because you have this infimum then.
Sorry.
Might, yeah, but I don't know. Yeah. Yeah, so this is an SDP. Let me just write semi-definite program. So to finish, I want to finish this example of the 5 cycle, just to have the story round. So we can now try to compute the Lovastatin number for the 5 cycle. So what you do is you take A to be the adjacency matrix of C5, and then you take as your matrix M, you take something clever. In this case, I take the all ones matrix minus, let's have a look, a half, 5 minus square root of 5 times A. So it's not so hard to check that you have the ones in the right positions to be feasible. And then you can compute the largest eigenvalue of this. And it turns out to be square root of 5. So the largest eigenvalue of M is square root of 5. So this is upper bound on Shannon capacity of C5, and this is actually tight. We've seen the example in the first lecture. So this is at least square root of 5. Yeah, so C5 can be solved. If you now go to C7, then we don't. Then we cannot match the upper and lower bounds. Good. So I think I will not do any proofs about Lovastatin number. So if you want to show that this is multiplicative, a nice way of doing it is by semi-definite programming duality. Okay. So let me just mention that. Maybe thinking about when to do the break.
Whenever it's convenient for you.
Maybe we just do it now. Yeah. If there are questions, we can do questions.
Is there any structure in the asymptotic spectrum? It's not a vector space. Is there any operation?
Well, so yeah, that's a good question. So in some sense, you want there to be, well, how to say this? So not really. But what I wanted to say is you don't want there to be any redundancy in the. So somehow we put a lot of properties on this asymptotic spectrum, right? We wanted it to be multiplicative and additive. And this removes a lot of redundancy. Yeah, that's just one remark. Right, you don't want there to be an easy way of constructing new elements from old elements. If there's a somehow you don't get new information from that.
Yeah, no, but he's asking whether if you have, forget redundancy, if I give you 2, can you generate from them a third?
Yeah, no.
It doesn't look
No.
Reasonable because you shouldn't be adding or multiplying them, right?
Yeah. Yeah. Yeah, that's a good question. But there might be some clever way of.
So do you know any example of an asymptotic spectrum of something which is finite but not one?
Yeah, that's a good question, and the answer is no. I don't know.
So it's possible that Buch and Cox didn't need to prove their theorem. Maybe it's either always one or infinite.
Yeah, we should think about it, because I haven't really thought about it. But it's maybe. Maybe there's an easy way of doing it, but I don't know. Yeah. Yeah.
Does it have a topology at least?
Yeah, that you can do. That I didn't do last time. We can actually. You can give this a topology by what you do for any element A in the semmering, any graph. You define a function A hat, which is an evaluation function that goes from x, the x of graphs or the x of S, to the reals. It takes an element and it evaluates. Now here you take a Euclidean topology.
Of course, this topology so that these are all
Continuous, yeah. That you can do. And then you get actually a compact that will make it a compact Hausdorff space.
So X is compact and Hausdorff.
With this topology. Yeah. Yeah, no, yeah. It's compact. So yeah. So you can take you can say a little bit more about this. So if your semmering is generated by a single element, then every phi is determined by its value on this single generating element. So then you can identify the asymptotic spectrum with a subset of the real. So you map phi to phi evaluated at A. Yeah, this uniquely determines phi now. And this will give you a subset of R. And this is a compact subset. So well, because where is it compact? I think because shouldn't that happen because all the A hats are continuous?
A has to be comparable to some integer.
No, I think there should be an easier way of seeing it. Let's think about it in the break. Yeah.
So, but if it's compact, then, for example, if you take the sequence of Hammer's bounds for all fields, there's a limit point. You know what it is?
No.
Okay.
That's exactly. Yeah.
Okay.
Yeah. Let's take a break. Okay. So we're going to look at tensors. Yeah? Are we all ready? Let's have a look. Let's just remove this. All right, so we've done graphs. So let's look at the other instance, tensors. So elements in the asymptotic spectrum of tensors. So so remember that. So this set is the set of maps from all tensors to the reals that are multiplicative under the Kronecker product, additive under the direct sum of tensors. They are normalized on these diagonal n by n by n tensors, so here they have value n on these guys, and they are monotone under this pre-order that I defined on tensors. So that's the goal, to find now elements in this set. Yeah, so I defined this pre-order. What I also want to define is, what I will use is isomorphism of tensors. So S is isomorphic to T if these three matrices are actually invertible. So if there are invertible matrices A, B, C, such that S is obtained from T by applying these three matrices. And I also want to use an approximate notion of restriction, which is called degeneration. And it's related to border rank, and it's given by saying that there are matrices, there are tensors S1, S2, a whole sequence converging to S, just with the Euclidean topology, say. And I want that for all I, Si is smaller than T in the usual pre-order. Yeah, so I just define these two extra notions on tensors. So we've seen already 3 points in the asymptotic spectrum of tensors. These were these flattening ranks. So you take your tensor, you group together two of the three indices, and then you get a matrix, and then you take its matrix rank. And there are 3 ways to do this grouping, so you get 3 functions. And these 3 functions are in the asymptotic spectrum of tensors. But so what we're going to do today is we're going to look at a family zeta theta. So it's parameterized by this theta. These are the Strassen functions. And a third family called the quantum functionals, written as f theta. And so these will be in the asymptotic spectrum of oblique tensors. Maybe let's not write it. So we're going to use it. We're going to look at these functions and maybe write here that this is in the asymptotic spectrum of all tensors over the complex numbers.
So this is from your work with Christian.
Yeah. That's right. So that's the goal, to have a look at these functions and to understand them a little bit. So the first thing I want to discuss is entropy. So many people know entropy, and maybe some people don't know entropy so well. So entropy.
May I ask just a quick question before?
Yeah.
So with regard to the sort of, for instance, the definition of invertibility there, I mean that also depends upon the field.
Yeah. Yeah.
So,
Yeah. That's right. That's correct. Very good.
So you just have to be paying attention.
Yeah, you need to fix a field before you start doing anything. You fix some field, and then you start doing your stuff. Yeah, and some things only work over. So here we only know how to do it over complex numbers, and this will make a difference. So asymptotic rank might change. We don't know. But asymptotic subrank might change. Okay. So entropy. So what you do is you take a probability distribution. Yeah, so
we want to use these points in the spectrum to prove lower bounds on tensor.
Yeah, good. Okay. So you can. So take any of these. Well, I have to be more precise about this one. Yeah. But if you take a phi in the asymptotic spectrum, then phi will be a lower bound on asymptotic rank, and there will be an upper bound on the asymptotic subrank of tensors. Yes.
How is this related to usual rank?
The asymptotic rank? So it's the, yeah, exactly. Yeah. So entropy. So you take a probability distribution, P, and yeah, so these are non-negative real numbers summing to 1. And let's just say that there is a, let's say there are rational numbers, and let's say there is a natural number n, such that all these guys are actually natural numbers when I scale them with n. Then I want to take the multinomial coefficient n, choose n times p, which is defined as n factorial and p1 factorial and pd factorial. Yeah, which is like the number of strings in d to the n with type p, yeah, with empirical distribution p. Now the point of entropy is that it measures how this grows, this quantity. So if I take this multinomial coefficient, I let n go to infinity, then this is upper bounded by, so this is always upper bounded by 2 to the power n times the entropy of p, and it's also lower bounded by 2 to the power n entropy of p minus a little bit. Yeah, so the entropy is really what happens asymptotically with multinomial coefficients. That's actually the only thing you need to know about it. Of course, I can give you the formula for it, but I don't think we actually need it. So let's do it like this. All right. So let's have a look at the Strassen functions. So I take tensor T, and then I take its support. So these are the triples of indices where the tensor is non-zero. So this is the subset of this product set. Now I take theta to be a probability distribution on 3 elements. And now comes the definition of the function. So zeta theta at t is a minimization over all s that are isomorphic to t of a maximization of this function here, which is in terms of entropy. So it's an average, a theta weighted average of the entropy of pi, some probability distribution. So I goes from 1 to 3. So what are these pi's? They are the 3 marginal distributions of some probability distribution on the support of S. Alright, so yeah, so we minimize over S isomorphic to T. Then you look at the support of S. You look at the probability distributions on this support, and then you maximize this function over it.
So what happened if we did it just for 2 matrices? That would be a simpler object, which we probably not.
If you do this for matrices, then you're supposed to get rank.
Yeah, you're supposed, but it's not obvious that
it's not immediately clear, but yeah, it should give you rank.
for every set,
Yeah, I can tell you. So if you take theta,
Half.
Well, if you take it maybe on only a single, so theta is in this simplex. If I just take all weight on one element, then I get one of the flattening rings.
Yeah, so suppose you take it half.
Suppose you take it half-half. Then I don't know. Then you. You should. Yeah, I think you will still get rank.
Somehow get the rank out of this.
Yeah.
Sort of really bizarre way to define the rank.
Yes.
Is it easy to define as entropy?
So actually.
Oh, you want me to write down entropy? Yeah,
no,
sorry. Yeah, let me write down.
I'm just thinking, suppose the matrix is fully supported, obviously it can be,
You diagonalize it to make it support small.
This is the definition.
So when you say probability distribution,
okay,
it's
because
what?
you
It's
do
just like a
all,
set.
I see.
It's a subset of this.
Yeah, but
Basically the point is.
It's a set. The support is a set of triples.
it's just a set.
Yeah. Yeah.
So, yeah, I guess that's a really good point. I mean, in matrices, it's probably also in tensor. You diagonalize or you use the equivalence to make it a diagonal matrix of the rank, and then the distributions will be such that it will be uniform here or uniform here, and then it doesn't matter which convex combination you take, you always get the.
Yeah.
But for tensors, you don't have enough dimensions to diagonalize, right? You only have these three matrices.
Right.
Yeah. But you do have enough in the asymptotic sense to diagonalize, because that's some other definition of.
In some sense, so we're going to see how this works over the complex numbers at least. So this is the definition, which I hope is clear. And the statement is that this is. Let me write down the statement. By Strassen. Zeta theta is submultiplicative, additive, monotone, and normalized. Alright, so that's not so good if you want to get, well, yeah, that's just the way it is. Okay, so this is good if you want to have upper bounds on asymptotic subrank of a tensor. This follows already if you have submultiplicativity. And so I can give an example. Let's do an example with the so-called W tensor, which has a very simple support.
It's the one I showed.
Yeah, it's also the one you showed, and I think I've also showed it last time. So the support is 1, 1, 2, 1, 2, 1, 2, 1, 1. And now you might be interested in the asymptotic subrank of this tensor, and then you can try to upper bound this using these support or these Strassen functionals. Now, what you should do in this case is you should put this theta to 1/3, 1/3, 1/3, and then I'm not going to do the maximization for you, but what will happen is that it maximizes at the uniform probability distribution. Yeah, so we need to maximize now over p on the support. So meaning I need to give some weight here, some weight here, some weight here. Turns out that that this function maximizes on the uniform choice. And so what happens then? You get 2 to the power uniformly weighted average of these entropies. So if you put uniform distribution, then what happens with the marginal distributions? Yeah, so what the first marginal, I put, so it's 1/3, 1/3, 1/3. Look at the first marginal, it gets 1/3 plus 1/3 on 1, and it gets 1/3 on 2. So the first marginal is a probability distribution 1/3, 2/3. And I take the entropy of that, and if you look at what this is, you get like 1.88. You get some interesting number. This turns out to be tight actually. We'll see a little bit about this later. Yeah, so I think what I want to do is did I use that board? No, I used that one. I want to relate this to slice rank. Yeah.
You are not going to make it multiplicative.
Sorry?
You are leaving it as sub-multiplicative.
I'll say something more about it later. Yeah. So let's try to prove that it's an upper bound on the asymptotic subrank of T. And so Strassen proved this, yeah, because Strassen proved these all these properties here. Where is it? Here. But I would like to give a proof of only this, and I want to do it via slice rank. So what is slice rank? The slice rank of a tensor T is a minimum over a sum of flattening ranks. So I take R1 of some tensor X plus R2 of some tensor Y plus R3 of some tensor Z, where X, Y, and Z sum to T. So yeah, these were these flattening ranks. So I'm taking this tensor X and I flatten it to a matrix, and but this one I flatten differently, and this one I flatten differently, and then I take the ranks and I sum them up. That's the slice rank. You go over all these decompositions. These are not direct sums. These are just element-wise sums. Now, slice rank is not submultiplicative and it's also not supermultiplicative. So that seems pretty complicated, but you still use it to do something useful. So, Terence Tao came up with this slice rank, and what he showed is that the subrank of a tensor is upper bounded by the slice rank of a tensor. I'm not going to prove that. He has a nice proof. Then it follows immediately that if you take if you look at the asymptotic subrank of a tensor to the power n, then this is upper bounded by the slice rank of t to the n. I just replaced t by t to the n, and asymptotic subrank is multiplicative on powers. Yeah. Now, so I also don't want to prove that really because I already said it now. The third thing I want to look at. So now slice rank. I think this is insightful to look at this. Slice rank of t to the power n is at most zeta theta of t to the power n plus little of n. Okay, for any theta. So this is what I want to look at.
Before this, maybe we should say that I mean, it's very hard to just this definition, but if it's the diagonal tensor, just a tensor which has a few ones on the diagonal and zeros otherwise, let's say R1s, then the slice rank is R.
Yeah.
And that's easy to prove by that.
Yeah.
Yeah. So that's really useful that we understand the integers in this scenario.
Yeah. And then, so if you have that and you know that slice rank is monotone, you prove this. That's exactly yeah.
This is related to the set game or to the concept. This is where the slice rank
Yeah.
first came up in the study.
Right.
And concept problem this way.
That's right. Yeah, so let's try to prove the third item. So the definition was that we have a minimization over S isomorphic to T, and then a maximization over P a probability distribution on the support of S, and then the function I'm looking at is 2 to the power this weighted average of the entropy of the marginals. Yeah. So now let's take S to be a minimizer. I want S to be a minimizer and I want P to be a maximizer of this in this optimization. Now we look at S. Let me write S just in this.
What you are going to get is the decomposition X, Y, and Z, right?
Yeah.
Yeah, you are starting from this.
Exactly.
Yeah, okay.
I start, yeah. I'm going to get an upper bound on slice rank of this power. So S, let's write it in the standard basis. So it's a sum over the standard basis elements. These are the entries of the tensor. And I'm going over all ABC in the support of S. But now I want to take S to the power n. So what happens if I take S to the power n? I get the sum, yeah, I get all these products. So S, A1, B1, C1, S, A, N, Bn, Cn. And here I get these basis elements E, A1, tensor, dot, 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 tensor E, An. The same for the B's and the C's. So A goes over n tuples now. Same for B, same for C. Yeah, I just wrote down what it looks like.
Now the tensors are d1 by d2 by d3 and n is something else. Yeah.
Yeah, S is d1 by d2 by d3. N is something large. Now, the way you should think about what's happening here is that each summand in this sum corresponds to taking n samples of in the support of S. Yeah, I'm taking, yeah. So I can think of a triple in triple ABC. I can think of it as like an empirical distribution on the support of S. Yeah, and so ABC is like an empirical distribution on the support of S. Then A is like a marginal distribution. I can think of it as a marginal distribution. And same for B and the same for C. And then I can take their entropies. It's maybe I need some more space for this again. Yeah, so ABC are just strings, but I want to think of their empirical distribution and think of it as a probability distribution. And then I can take their entropy. So I can take the entropy of A, of B, and of C. No. So, let's see. So A, I look at A as a string. And then I just count how many ones are in the string, how many twos are in the string, etc. That's the empirical.
Oh, sorry.
Yeah. Yeah. So that way I want to think of ABC as probability distributions, and then I can take their entropies. So, but this is the marginal distribution of some probability distribution on the support of S. And how did we pick P? That's now important. We pick it as a maximizer of this function. So what will happen is that either this one or this one or this one will be smaller than the average of these three, and also the average of the maximizer. That's how we pick P. Okay, this is maybe a bit fast, but this is some of the clue here. So since we picked P to be a maximizer of that function, I now know that one of these three entropies has to be smaller than this average of marginal entropies. And this I'm going to use to split up my sum. And so S tensor n is this big sum. I'm going to split it up in 3 sums. What you do is the first sum goes over all the ABC where the entropy of A is smaller than this. The third sum you do the same, but then for B. And the third one you do the same, but then for C. Yeah, so I'm splitting it up according to whether the h of A is small, whether the h of B is small, or whether the h of C is small. So and now I claim that the flattening rank of this guy is small, the flattening rank of this guy is small, and the flattening rank of this guy is small. And the reason is that you can now look at how many A's actually have this property, and they're not. And if you want to know how many there are, so so from this guy I want to know the first flattening rank, and it's upper bounded by how many A's there are for which the entropy is small. If you count this, you will end up with that this is at most some polynomial in n times 2 to the power n times this weighted average. Right, and this is the support or the Strassen functional. Okay, so this shows that this is like a polynomial times the Strassen functional. You do the same for the other terms.
So this is all in Strassen's paper. I mean, he already did slice time without even knowing.
Yeah, so he did not.
The same argument that goes in the capsule.
No, so this is the argument that comes from the capsule. Strassen doesn't look at slice rank. He does it. He proves it without looking at this. Yeah.
But the motivation for choosing these functions is,
well,
is not this. I mean,
no. Well, I don't know.
He wants to bound something smaller, which is a subrank. But so you just say that. But the bounding of the subrank does not go in. Does not use flattenings.
I don't know what his motivation was. It's not completely clear.
In the proof. In the
Yeah.
proof I mean, he needs to prove
His proof is
the same type
yeah.
of result, but
Yeah.
for subrank, and there are no flattenings. It's marginal, don't it?
You mean not in this? Yeah, not in this way somehow. He really it's really an information theoretic argument using entropies and.
Yeah, but the subrank is defined as sort of like a reduction to a diagonal tensor.
Mm-hmm.
And it seems very similar.
But what's your question?
No, I'm not. I'm just wondering if it's the argument you just gave must be somewhat implicit in Strassen's.
Yeah, I couldn't recognize it in his paper.
Okay.
Yeah, this is much shorter than what he does, I think.
Okay.
But I did not prove all the properties, but this is really a shortcut. If you follow his paper, if you follow the proof in his paper, then you'll be talking for many hours. Yeah, so this is just to give you an intuition of what's going on. Why do these entropies occur? Why are they relevant? It's because you take this power and then you start doing some kind of statistics on the sequences that you see, and that's why you get these entropies. You want to measure, you want to count somehow how often certain strings occur, and you want to fiddle around with it. So this is just to give you an example of how that goes. But
so when you say these numbers, this S, A, B, C, etc.,
yeah,
they can be positive or negative, or
yeah,
something.
Yeah.
But you really look at the support.
Yeah, this is all about the support. Yeah.
Yeah. When you are actually counting these statistics, you don't care about this number.
Yeah. But we cared before because I took this. I did this. I take a minimization over. There you do care.
Right, but that's the point of tensor. You don't care about it. You just want to write it as a combination of few tensors
Yeah.
with whatever coefficients you want.
Yes.
So that's where it comes in. It's only simple.
Okay, good. So, make one remark about this. Quick remark. So, so I mentioned that these are only submultiplicative. Now, if you restrict to a subsammering of so-called oblique tensors, then they become multiplicative. So let's maybe not define what oblique tensors are, but let me just state this. So there is an interesting subsammering of tensors called oblique tensors over F, and there they become actually multiplicative. Okay. Now, so why is it so interesting? It's interesting because of this subsammering theorem that I mentioned earlier. This is a subsammering of all tensors. And now you see that we have these elements in there. This is an infinite family. By the subsammering theorem, you get that there must also be an infinite family in the asymptotic spectrum of all tensors. Okay, that's just good to know. It doesn't tell us how to get them. But so what we're going to do now is see what they look like over C, over the complex numbers. So that's the next thing. So this is the quantum functions. Yeah, they're called quantum because we thought about quantum entropy, things like that when we define these. So let me give you a definition which is kind of easy to understand. Let me try. So you take a tensor S, maybe a bit more precise. Okay, I want to define moment polytopes in some kind of understandable way.
So maybe you want to say
Yeah?
that all these Strassen functionals, which would be lower bounds on tensor rank,
Yeah, yeah.
in the oblique case, or when you extend them, the value on an n by n by n tensor is at most n.
Yeah.
So they would not give any use for.
Yeah. They're not useful for this, and it's yeah. So what happens is that these zeta thetas are always smaller than these. So they're not so good for asymptotic rank. If you want to understand asymptotic rank, it's better to just use these. Yeah. So I'm now going to define this family of functions, which is in the asymptotic spectrum of complex tensors. And I want to use the moment polytope to do this. So how does this work? You start with some tensor S, complex tensor now. And then I take a flattening. Let's say I flatten the second and third together, so I call that S1. That's a matrix. Now, of this flattening matrix, I can take singular values. Let me call them sigma 1, sigma 2, etc. These are real non-negative numbers. And then I want to turn these guys into a probability vector. So how do I do this? And I want to call this the spectrum of S1. And I do this by squaring them and then normalizing. So I take the squares and then I divide by the sum. The squares. Yeah. So this is now a probability vector. And I can do this for all three of the flattenings.
Maybe for some people who know quantum information theory, it's not very important to know, but if you take S1 times its transport, you get a square matrix, or size D1. This would be, if this was if this tensor represented some three-partite quantum state, this will be the interaction of the first player with the other. Anyway, it would be a density matrix. It would be just a quantum state. And this would be just so it's a positive definite matrix. And these numbers would be the eigenvalues that will
that comes, yeah.
But anyway, it's not that the real definition is extremely natural definition.
Yeah.
That's what I mean.
I thought singular values was.
Here the flattening is a partial trace. No, not everybody knows it, but those
yeah.
who do.
Yeah. So the moment polytope of a tensor T is a collection of triples of such spectra. So you take some S, and then I take the spectrum of S1, the spectrum of S2, the spectrum of S3, and I go over all S in the same space as T, which are degenerations of T. So they're smaller than T, and then that takes some closure. That's the moment polytope. Yeah, so it's pretty complicated because you have to go over all these S that are smaller, and then you look at all these probabilities that occur, triples of probabilities.
So there are two non-trivial statements. A, that it's linear. I mean, the fact that it's a polytope. It's convex and it's linear. It's a non-trivial statement.
It's a convex polytope. Yeah, that's a non-trivial statement. I'm not really going to use this, but that's a very interesting fact about it. And there is a dual description of. There's a dual description of this object, which is important. So I want to mention that quickly, and then define the quantum functions. Yes, and then I want to move to these combinatorial aspects. Right, good. Yeah, let's try to look a little bit at the dual description of the moment polytope. I can't really do it because you need a lot of background if you really want to get into it. But I want to relate a little bit to the statistics that we were doing before. So let's do this. So let's try. So this is, I call this like a flattening spectra description of the moment polytope. And now I want to look at something called Schur-Weyl description. So let's try. Let me try. Yeah. Okay. So what we did earlier in this proof with the slice rank, what we kind of did is we looked at T to the n, right? And we somehow decomposed it, and we looked at what kind of types occur. So you can also write this as, well, you have some tensor T in CD1, CD2, CD3. I'm changing my notation a little bit. So this used to be CD1, D2, D3. It doesn't matter much. I want to just explain it a little bit. What we did was we take a high power of T, which lives in this space. Nth power of T lives in this space. And then what we looked at is, we looked at, okay, I take now CD1 to the n, and I can write it as a direct sum over these n tuples of these one-dimensional spaces. I can decompose this. I can just look at the standard basis. Yeah. Now this you can do for all three, and then you can expand the direct sum. You get one big direct sum. So you get a big direct sum over triples. That's what we did before, more or less. And yeah, you get these. And then the B's and the C's. And you get this decomposition. Now we want to do something different. And the difference is that we're not going to look at this decomposition. We're going to look at a better decomposition from symmetry point of view. And this is something I will not really explain, but it's a different decomposition of this space as a direct sum of subspaces, which I denote with these square brackets and then subscript lambda, where lambda goes over all partitions of n, integer partitions of the number n with at most d1 parts. Now, what's the property of these subspaces? This subspace have a nice property. That's somehow we look at them. And the property is that they are invariant under the action of the symmetric group, first of all. So the symmetric group acts on this space by permuting the n copies of these spaces. And these are invariant under this action. So you take something in this subspace, in one of these subspaces, you act with the symmetric group, you stay inside. That's one. And the other is they're invariant under the action of the general linear group. So the general linear group, GLD1, it acts on this space by acting on each component similarly, with the same action. If you take something in this subspace, you act in this way. With the general linear group, you stay inside. So that's, these are really the basic properties of these subspaces.
But we also really want that because the definition of equivalence of tensors is with respect to the...
Yeah, so you're saying it's very natural.
Very natural, yeah.
Yeah.
It would be said.
That's right. So that's very natural because, so now, what you should do, or how you should think about this, is that you take t to the power n, and you want to decompose it according to this decomposition. So you want to write this as a sum, a direct sum, or just a sum of the projections of t to the n on these components. Yeah, so I do this decomposition for each component. So then again we get, instead of triples of like this, we get triples of partitions. And then when I take a tensor t to the n in here, I can decompose it according to this decomposition and see which triples occur. Yeah, on which components is my tensor non-zero, and so these are these projections on these triples. So let me tell you the very surprising and not so easy to prove dual characterization of the moment polytope of T due to mainly Mumford, I think. And it's the closure of the set of triples lambda divided by n, mu divided by n, nu divided by n, where lambda, mu, nu are such that there is some n, such that t to the power n on lambda, mu, nu is non-zero. So yeah, I take t, take it to some power, I see lambda, mu, nu occur, or my tensor is non-zero on this component, and these guys normalized I put in my set, and then I take the closure. This is, you should think about this as a Euclidean object in Euclidean space. Take Euclidean closure, and I get the same polytope. So that's very surprising. So here, so earlier I defined this using singular values, and now we have this this weird characterization using the types that occur in the decomposition.
So in the first definition, is this stuck to S isomorph? Can you pull out the subset of it without the closure?
You mean want to make this non? Yeah, right.
I mean, is there a way to modify this a little bit so that the two are kind of equal without taking the closure on the side?
I'm not sure.
Not sure, but you may get something non-rational in the spectra anyway. The spectra may be non-rational. These are all non-rational numbers.
Yeah, that's already right. Right. Even if you put isomorphic or smaller than
I think it's maybe Kliatschko is the guy who actually.
Okay.
Maybe yes.
Yeah, I'm not.
Based on
yeah. Brion has some interesting work on it too. this is the moment polytope, yeah, complicated object. Now we're going to define our quantum functionals using this complicated object. Yes, let's do that. Time.
The exist n. I'm confused about the exist.
Yeah.
I mean, there's an n
So.
already in the expression.
Yeah. How to say this? Okay. So whenever these lambda mu nu exist, there will be partitions of. There will be. There will be probability distributions once you divide them by n. How to?
The lambda mu nu are enlarged by a factor of n. So they're d1n. They're partitions.
They're partitions of n. Let's just say it like this: there exists an n, and there exists lambda. Yeah. There exists lambda mu nu, partitions of n.
Here they were partitions of. Here they're already partitions of.
Such that this holds, and then you put.
Yeah, if you erase the exists n.
Maybe this, like this.
No, but
This whenever this.
they have partition, yeah. Oh, when it's the nth power, yeah.
Yeah. When it's the nth power, there will be partitions of n.
But now you're taking
So you take the union. I mean, you take the union over all n.
Yeah.
And
Yeah.
then
You take the whole.
yeah.
Yeah. N is inside. Yeah. O n.
So you also know the saturation conjecture, but maybe that's not actually important.
Yeah.
I don't
Yeah.
know the saturation conjecture for this.
We don't know the saturation.
No, these are the Kronecker coefficients. They are not the.
They're not the leverage.
They're not.
Okay. Let's do. So let's define these functions. We again have this this parameter theta, which is again a probability distribution on 3 elements. I take my tensor T, which is a complex tensor, and then I define f theta on T as a supremum of 2 to the power, again, a weighted average of entropies. And now these come from the polytope of T. Okay, so it's the same function, but now we're going over this this moment polytope.
So this contains a source function.
In some sense, and so let me tell you. Yeah, I will tell you how. Yeah, let's first. Yeah, so these are in the asymptotic spectrum always for all complex tensors. So let's not go over the. So I had a short intuitive thing, but let's not do that. So let's say something about the Strassen functionals. How does it relate to these Strassen functions? So what we know is, in general, they're upper bounded. By the Strassen functions. We have a class.
So they are worse for tensor law.
Yeah, they are definitely worse. Yeah, and these were already bad. But they're good for asymptotic subrank.
Yes.
Yeah? We have a subclass which is called free tensors. If T is free, it's an easy definition, but let's not do it. Then we actually know that they're equal. Free includes oblique, which is this other family I mentioned. Yeah, so
That includes matrix multiplication.
yeah, also. Yeah. And one final interesting thing is that you can define an asymptotic slice rank. It's a priori not clear whether it exists or not, because slice rank is not sub and not super multiplicative. But it turns out over the complex numbers it actually exists, and it's actually the minimum over the quantum functions. Yeah, so these are just 3 interesting facts relating to the stuff we talked about earlier. Are there any questions about quantum functions? I want to say something about combinatorial aspects, but if there are any questions, then let's do that.
Just one question. I mean, it seems like a quantum generalization of Strassen's classical probability distribution.
Yeah.
And if you think about it this way, it seems like the diagonal. So if you forget the GLD action, right? You just look at the subgroup of diagonal matrices, the tori action, which are just part of the action. This is sort of classical scaling, and it seems that, or I'm guessing that Strassen's functions will come out of this subgroup.
More or less, yeah, except that you have to minimize over how you take the torus, I think, something like that. You see what I mean? You're saying, oh, replace GL by the torus.
GL by the torus.
But the torus, of course...
You're just scaling the lines, not...
Yeah.
And
I think it's a good intuition, yeah. There's something extra you do. You have to minimize somehow over how you take the torus, I think. There's not the, I mean, there are multiple.
Yeah, it's not problem. Yeah.
Okay. So, yeah, that's pretty quick. It's very hard to get a good feeling for the quantum functions, but so this is the best I can do now. This is the definition, at least. And I want to say something about combinatorial aspects. Or hypergraphs. So somehow I want to have a closer look at the asymptotic, the subrank and the asymptotic subrank in a combinatorial way. So what do I mean? So I simply mean that instead of focusing on the tensor, I want to focus even more, but now like somehow relating to these properties on the support. So the support I want to think of as a hypergraph. So the support, yeah, if T is some n1, n2, n3 tensor, then this lives in this product space. So let's make this precise. So I want to look at something, let's call it a 3 graph, or 3 uniform, 3-partite hypergraph. I define this as just a subset phi of a product set, where these are finite sets. Think of it as a hypergraph, 3-partite. And these are the 3 parts somehow. And every edge goes through each part. Phi is a matching if all the edges are completely disjoint. Take A different from B, then they are different at each coordinate, each of the 3 coordinates. Yeah, that's a matching. So yeah, so an example of a matching is, for example, the support of these diagonal tensors. That's an easy example. This is a matching, but you can also take some permutation. So like this is also a matching.
But after permutation, they have to look like this.
Yeah. Up to a local permutation, they will look like this. That's right.
Just like matchings in graphs.
Yeah. Yeah. Exactly. Now, so when is, say, psi is a subset of phi, and phi is a 3 graph. When is psi induced? Well, it's induced if we can obtain psi from phi by intersecting phi with like these marginal sets, psi 1, psi 2, psi 3, where psi I is just all the ith elements of any element in psi. I go over all elements in psi and I check the ith coordinates. Yeah. This is, so you know this from graph theory, like induced subgraph. This is like an induced 3 graph. That's the other thing. Now let's study something which I maybe call the subrank or the induced matching number. Q of phi. So what is that? It's the size of the largest induced matching psi in phi.
So it doesn't have to be. So in bipartite graph, what would be the difference and the maximum matching in this bipartite graph? Would be the maximum matching in this bipartite.
Yeah.
Sorry, it would not be induced. So sorry. Yeah, it's much smaller. It can be much smaller than the maximum matching.
So I give you an example.
If you take a complete bipartite graph, then you get only one element, I guess. Yeah. So it's much smaller.
So now this I want to study, but asymptotically. So we define a Kronecker product on these 3 graphs, and it should remind you of tensors. This goes over all A in phi and all B in psi. And I pair them up such that they become triples again. Yeah, so this is.
I don't know. You are doing it for 3 graphs. Is it well understood in graphs? Everything we are doing.
I'm not actually. I don't.
Even just the induced maximum induced.
I don't actually know. I don't actually know.
It's much simpler.
Yeah, I didn't actually thought about it.
Theory will apply that as well. So.
Yeah, I had. I thought. Okay, I think. I had the feeling it became very easy, but I forgot.
Okay.
I want to stick to 3 graphs. So I define now the asymptotic induced matching number, yeah, which is the supremum over n of q of phi to the n 1 over n. Yeah, that's what I mean. So that's the asymptotic variation I want to study. But it's not completely isolated. There is a direct connection with what we were doing before. So let me mention this. Namely, if you take a tensor T and you take its support, this is very easy observation, then the subrank of the support, defined in this hypergraph way, is at most the subrank of the tensor. Yeah, because if you find this matching in here, you will actually find like a subtensor. You find induced matching, then you will actually find you will find a way of making a diagonal tensor out of this, of that same size. Okay, so that's one. The other thing is that if you take the support of S times T, then it's the same as the support of S times the support of T. So this definition behaves well with respect to support. And the third thing is, this now follows it, asymptotic subrank of the support of T is at most subrank of T. This is what I want to tell you. Because, so now we can use this in 2 ways, this statement. So either we start with some 3 graph and we're interested in its asymptotic subrank, then we should just find any tensor with support that 3 graph. And we can actually pick the field and we can pick the coefficients. And then we can try to get good upper bounds on the asymptotic subrank of a 3 graph. So that's one direction. The other direction is that you have a tensor and you want to get good lower bounds on its asymptotic subrank, and you can do it in this way. Yeah, so that's, let me finish with that. So if you have some 3 graph phi, you can get an upper bound by minimizing over the field, minimizing over tensors over this field with support of t equal to phi, and then minimize this q tilde of t. Now, so this we have a handle on via the support functions or the quantum functions, yeah? So that we can use to upper bound this. But here you still have a lot of freedom. I don't really have time to do it, but you can. This is the way to solve this capset problem. It's exactly the way to do it. I think I should not do it because it will be too long. Let's see.
This is polynomial time algorithm?
No.
Yeah, I don't think so, but I don't know if there is one kind of possible.
It's not clear. Yeah. No, it's not clear at all how to deal with this, because there's this choice of field, then there's the choice of the coefficients of t.
No, fix the field though.
Fix the field.
Is it, or is it, I mean, slice rank itself, is it computable? Is it, given?
Yeah, but you don't need slice rank. Is not. You should take slice rank of a power of t, not.
Yeah, I know, but suppose we are just looking at slice rank of tensor. Is this easy to compute?
I don't know. Yeah, it's a good question. What I want to mention maybe about this finally is that it's somehow similar to the Hamer's bound. You could think about this as the tensor generalization of the Hamer's bound. Right there we also had this choice of field, and we looked at the rank of matrices, which we tried to minimize, and we had a certain zero pattern that we fixed. That was the Hamer's bound. Here it's the same, but except that we don't do rank, we do asymptotic subrank. You go over all these fields, you go over these tensors with certain zero pattern. So here's a question: what's the tensor generalization of Lovastatin number, for example? Yeah, it's not clear. Yeah, I think it's enough for now. Thanks. Yeah.